We are now looking at a teaching video on the applications of integration plane area. First, we look at a simple definition of what plane area is. So, a plane area is basically the area under the curve bounded by two limits, and it has to be above the x-axis. So, if I'm finding a definite integral of a given line, then it will be the same as saying finding the plane area bounded by first the limits and then the curve and the x-axis. So these three parts actually constrain an area. That area is called the plane area bounded, or the bounded area. Let's look at this case here. Now we have a straight line. The equation of the straight line is y equals 12x plus 5. So these two vertical lines form the limits, x equals to 2, x equals to 6. So when I'm looking for the plane area or the area bounded, it will be this area. So there are two ways to do it. So I'll first look at the way we normally do without integration. Since this is the shape of a trapezium, so the area of a trapezium is given as half times the height times the sum of two parallel sides. These two limits, or these two vertical lines, are the one A, the other one B. So to find that length, I will have to put in x equals 2 in there. So 2 times 12 is 24 plus 5, 29. Next is to find this length here. I have 6 times the 12, 6 times the 12, so I actually would have 72 plus 5, 77. So to find the area of the trapezium, I will have half times the distance here is 6 minus 2, that is 4. And I have the sum of 29 and 77. So the final answer is 212 units squared. By using integration, I'll do it over here. Let me just put in the simple form first here. The area would be the integration from 2 to 6 of this function, 12x plus 5 with respect to x. So for the full working, I'll do it here. Area is equals to the integration from 2 to 6 of 12x plus 5 with respect to x. When I integrate 12x, I look at this index 1. So I increase that. That will be 12x to the power of 2, then divided by this index 2. The 5 is basically 5x to the power 0. So I increase the index by 1. So I have x to the power 1 divided by 1 here. So to simplify the expression, I have 6x squared plus 5x. The upper limit is 6, lower limit is 2. So I will take the upper limit 6 and make substitution into the expression. So 6 times 6 squared plus 5 times 6 minus 6 times 2 squared plus 5 times 2. So 6 times 6 squared plus 5 times 6 minus 6 times 2 squared minus 5 times 2. So the answer is 212. So for straightforward plane area bounded by perhaps straight lines and limits and also the x-axis, we can do it in two ways. One is using the formula of the geometric shape. In this case, the area of trapezium. But we can also use the idea of integration. Now, the idea of integration will help in more cases, especially if you have got a curve here and the plane area under the curve can only be found by integration. Now we consider the third point, definite integral taking limits from the x-axis. So when I say taking limits from the x-axis, I'm looking at the x-axis and the two limits here, x equals to 5 and x equals to 7. So the area I'm looking at is this area. So first, this area is bounded by the two limits, the curve and the x-axis. So to find that area using integration, it would be to integrate from 5 to 7, the lower limit is 5, upper limit is 7. The function is 1/3 x squared. So that is the expression I will integrate with respect to x. Next step is to go over this integration. 1/3 x to the power of 3, I increase 1 there. So I'll write it this way. in one fraction. So x to the power of 3 over, originally there is a 3. Now I divide the expression by a 3, the new index. So this can be rewritten as x to the power of 3 over 9. Upper limit is 7, lower limit is 5. The next step I'll be doing substitution. Put in the upper limit first, which is 7. So 7 cubed on 9 minus, I have the lower limit put in there, 5 to the power of 3 over 9. So 7 cubed divided by 9 minus 5 cubed divided by 9. I have 24 and 2/9 units squared. You can see if you are taking limits from the x-axis, then we'll integrate the expression of the function with respect to x. So the integration is to increase the index by 1. In this case, from 2 it became 3, and that 3, the index, will become the divisor. And then for the substitution, the upper limit is put into the result of integration, and then minus of the lower limit put into the expression here. So the difference will be the area bounded by the limits, the x-axis, and the curve. The next point, we're looking at point 4, definite integral taking limits from the y-axis. So the y-axis is here. This will be the lower limit, and this will be the upper limit. So to find that area, first we have to make x the subject. In this case, I will have x squared equals to 2y. Then to square root both sides, I will have plus or minus of square root of 2y. Now in this case, because this shaded area is above the x-axis, then I will be looking at x equals square root of 2y and rejecting x equals negative square root 2y. So to find the bounded area, I'll integrate from 2 to 18 square root of 2y with respect to y. So this expression is square root of 2 y to the power of half. So when I integrate that, I will have square root 2. I increase the index by 1, I'll get 3 on 2 over this index becomes a divisor. So to rearrange that, I have this expression, square root of the 2 y cubed and these 2 here over 3. So one more time, if you see 3 on 2 is basically 3 times half. So y to the power of half is square root of y. But I have the cube, so y cubed with the square root. And I combine square root 2 and square root y cubed. The 3 on 2 here, I have a reciprocal of 3 on 2. Basically, that will be 2/3. 2/3. Now I will make substitution. So first, 2 times square root of 2 times 18 cubed over 3 minus 2 times square root of 2 times 2 cubed over 3. So that would be 72. This will be 8 on 3. So 72 minus 8 on 3 will give me 69 and 1/3. So just go over this once more. If I want to take limits from the y-axis, then this equation, which has y as the subject, will have to be rearranged such that x will now be the subject of the formula. So that whatever the expression is of the x, now is in terms of the y, will be used in the integration to find area bounded by the 2 limits, the y-axis and the curve. Now we look at point 5, the sum of bounded area by separate definite integral. So what I mean by that is, you can see here we have a sine 2x curve. So this area, when I integrate from 0 to pi, will be a positive area. If I integrate this curve from pi to 2 pi, that will be a negative area. So if I want the 2 areas to be added up, I cannot take the integration from 0 to 2 pi, because this positive area will actually cancel off the negative area. So in the end, my result will be a 0. So in order to find the 2 areas and then to add them up, then I will have to do the integration separately. From 0 to pi, the integration of this function, pi to 2 pi of the integration of this function. But of course, I need to make some adjustment. Knowing that the area is going to be negative, I can do one of 2 things. One is to introduce a negative so that this area is reflected on top. Or I can take the modulus of the result I get here. Of course, the third way will also be, if I know these 2 areas to be the same, then I will find this area and then times 2. Then it will be these 2 areas. So what I'll do here is that I'll go for the last option, which is to integrate from 0 to 2 pi of this function and times 2. So this is how it will look. 2 times the integration of the curve from 0 to pi, and 2 sine x with respect to x. So that 2 can be taken out. So I will have this expression. Now I would integrate sine x. So when we differentiate cos, we get negative sine x. So to integrate then, I'll get negative cos x. Upper limit pi, lower limit 0. I'll substitute the values in, taking the negative common factor out, negative 4 then. I'll substitute pi into the x first, then 0. So change the mode to radian mode. So negative 4 times cos pi minus cos 0. I will have 8. Units squared. So when we talk about sum of bounded area, we have to be very mindful of the cancellation of possible areas. So especially if we look at this particular graph, this area is below the x-axis, then we know that there is an introduction of a negative area, and as a result, instead of having a bigger sum, it will be a reduced sum because of the cancellation. Now we look at point 6. Point 6 is about bounded area by differences of two definite integrals. Now in this case, you can see there is a straight line and a curve. And of course, this bounded area has a side here, y-axis. So this area is bounded by the straight line and the curve and the y-axis. Or we can also say for the y-axis, x equal to 0. And this is a redundant point since the curve and the straight line meet at x equals to 2. So to do this, what we can observe over here is the straight line function is all the time above the curve function from x equals to 0 to x equals to 2. So to find the area, what we can do is to integrate from 0 to 2 of the top function, which is x plus 2, minus the function below, x squared. So really, I will be looking to integrate from 0 to 2 of negative x squared plus x plus 2 with respect to x. So the integration now, add 1 to the index, I get negative x cubed, then divide it by the new index 3 plus x squared over 2 plus 2x. Upper limit, lower limit. Next is to do substitution. I will have negative 8 on 3 plus 4 on 2 plus 4 minus a 0 because if I put in x equal to 0 into each of these terms, the sum will be a 0. So the final answer would be negative 8 on 3 plus a 2 plus a 4. I have 3 and 1/3. So this bounded area is 3 and 1/3 units squared. So for this teaching video, we have looked at plane area. So whether the plane area is, we take the plane area by the integration taking limits from the x-axis or y-axis, or in this case, when the bounded area is enclosed by the straight line and the curve. So we have come to the end of this teaching video.